glad to be here. Well, today I'm going to be talking about a topic which is similar to the things that we have been talking about recently, which is computability, but still very, very different. Because my topic is related to inconsistency and inconsistent mathematics in general. So, since several of the speakers here come from a background in computer science and mathematics, which use classical or intuitionistic backgrounds, I will start a little bit on the logical background, which is paraconsistent, which you may not have heard a lot of. Right. Okay, so I think I'll have to click this thing. All right. So I'll be talking about naive set theory as a starting point. Some of the naive set theories we know about allow for inconsistent sets, and in particular inconsistent sets of numbers, which is an interesting topic if you think about from the perspective of computability theory. We may want to know if such sets of numbers might be decidable, right? So this would require something like a paraconsistent computability theory, which is something that we haven't developed. It's only a handful of people in the planet that have ever looked into the topic, some of which are even founders of this conference we're having, like Roudley and Meyer, for instance, priests, etc. So I'll be talking about that. I would like to sketch for you some toy model that might actually give us some intuitions behind this kind of questions. All right, and I will finish by pointing out some problems and some of the problems and questions. So maybe you have heard about naive set theories. These are characterized by the comprehension axiom, which pretty much tells you that every property determines a set. And of course, you also have the axiom of extensionality. And then when we have studied set theory, we all have heard that this sort of intuition is problematic. You might get sets like the Russell set, which at least classically speaking, is a problematic kind of set, right? It's something that leads to contradiction, and classically and even intuitionistically, that is equivalent to disaster, right? We have triviality in that kind of setup. So that led to people rejecting naive set theories based on this comprehension axiom, and then translate. We moved to ZFC frameworks and so on. Okay, so if you change the logic, then you can have this kind of axioms as background of set theory. Okay, and there has been some work about this. There are some naive set theories around. Some of them are negation inconsistent. Some of them are not. And this very much depends on the properties of negation and implication of the background logic. And to give you some samples, there's a paraconsistent logic called LP, which is the one I'll be talking the most about today. And which such a theory, whenever you have a pair of contradictory propositions, it is not the case that every proposition follows. So that's the hallmark of paraconsistent logics. Okay, and this is the kind of thing you need in an inconsistent mathematical theory. All right, so if you take LP as a background theory and put some this set theoretic axioms on it, you get this naive set theory. It's negation inconsistent, but LP has some downsides. So as Ben was mentioning earlier today, the conditional from LP won't obey modus ponens. So as you may imagine, the deductive power of this theory is very limited. Then on the other hand, there is a very important tradition from relevant logics. So Ross Brady worked a lot on this topic, naive set theories.
It's Jonty's talk. I have no idea how to listen to it on the phone. I have to mute someone.
I don't know how to get it on there.
So Raspberry worked a lot of
Just take nothing.
There's an important tradition, as I was saying in the relevant logics history. Raspberry developed this logic called DJ, which not only is very consistent and relevant, is also specially designed to handle the axioms like naive comprehension without following, without triggering Curry's paradox. Okay. So in Ross's framework, for instance, you can define things like the Russell set, but you will only get things like the Russell set is in itself if and only if it's not. And this won't imply the explicit contradiction, the set is in itself and not. Okay, so that would be a naive set theory, yet not negation inconsistent. All right, so this is some examples of the kind of set theories we have in mind. Since I'm interested in inconsistent sets and whether they are computable or not, I will be spending most time in, or frankly, all the time in inconsistent set theories, right? And I will focus on LP because LP is a very simple logic, a very simple framework we can work with and get some intuitions on the topic we want. All right. So I mentioned that LP doesn't have a detachable conditional. Priest has already proposed, Priest invented this logic. Well, he and other people like Asenjo, it's a debate. Okay, but Priest has already suggested that you can expand LP with a detachable conditional that doesn't have contraction, avoids Curry's paradox, and so on and so forth. But I will keep it simple for today. Just first order LP, and that's it. So LP is very much based on the same kind of language that we have in classical logic. Nothing special there. Okay. But what I really want to point out to you is the sort of models for first order LP, if you haven't encountered them before. These models are pretty much the same as classical models, but one special feature of this is that when you talk about the extension, the denotation, sorry, of a predicate, you have to assign two things to it. One, it's called the extension of the predicate. The other, it's called the anti-extension of the predicate. And intuitively, the extension of P is the things that satisfy P, and the anti-extension of P is things in the domain that don't satisfy P. So if you take that kind of approach, then whenever you have contradictions like something is P and not P at the same time, then the model can handle that kind of situation because you have this two independent ways to look at the property, and the extension and the anti-extension may overlap, okay? And another condition that these models have for extensions and anti-extensions is that they exhaust the domain, okay? So this is the only particular thing about the models that I want you to really know for this talk. Identity works in a very intuitive way, just like that. When we assign elements of the domains to the variables or the constants or the functions, things are very much standard, just as in classical theories. And then when you look at the truth and falsity conditions for formulas, the important thing to notice here is that, as I was telling you, an atomic formula of this form will be true if the denotation of the terms are in the extension of the predicate. And it will be false if the denotation of the terms are in the anti-extension, okay? So this kind of condition allows you to have inconsistency around. That's all you have to get from this. The truth conditions for the rest of the connectives are actually quite intuitive. Negation is true. if the negand is false, negation is false, if the negand is true, and so on and so forth. So those are the kind of models we have in mind here, LP first order models. Now, as I was saying, you can put on top of this kind of logic the axioms for naive set theory, okay? And think of a primitive two-place predicate, which I will be denoting with this epsilon symbol here, different from the other symbol I was using in the model theory, right? You can use a two-place primitive symbol for set membership between this binary relation between sets, and this relation is it behaves accordingly to this axioms from naive set theory. In terms of proof theory, what we really have here is a natural deduction system for LP, which consists only of rules and the axioms. So proof theoretically, it's not very interesting. I want you to think of this rather model theoretically because of some of intuitions that this will bring to the topic of my talk. Okay, so some properties of naive set theory based on LP. In 1992, Greg Restall proved some claims. In particular, he proved that this theory has inconsistent sets, like Russell sets, for instance. He proved the non-triviality of this theory using incidence matrices. And he also showed that all the axioms of set F are theorems of this naive set theory, except for the axiom of foundation, which makes sense because if you have Russell set around, then you might have non-well-founded sets. Okay. Now, when you have a naive set theory, the axiom of comprehension gives you or allows you to derive from it standard set theoretic operations. So you don't need things like the axiom of union or whatever, or the axiom of empty set. You don't need that. You can build that from comprehension, and you can actually build other sets like a universal set and other sorts of interesting structures. So for instance, you can build inductive sets. Normally, you would have to add the axiom of infinity telling you that there is some inductive set around. But we don't need to do that. We can have that from comprehension, right? And for the purposes of this talk, we'll be thinking about the von Neumann ordinals that are usually mentioned in set theories. Okay, this is going to be the thing we use today as a representation of natural numbers. We will assume that those are numbers here. And as a final remark on naive set theory, because you have unrestricted comprehension, you may define sets impredicatively, okay? And one of the most interesting impredicative sets, if not the most interesting, is the Raudley set, okay? This is a set of all things that are not in that very set, okay? And this deals immediately, X is a member of this Raudley set, if and only if it is not, okay? And with the logic we have in mind, this is also equivalent to X is in set and X is not in set for any X. So this set is universal. Everything is in it. And it's also empty. Nothing is in it. Both things hold in this theory. So this is like a maximally inconsistent set. It's even more inconsistent than Russell's set in a sense. And I'll be using this today a little bit. If you think of it in terms of models, then in a model for this kind of set theory, the extension of this set would be the whole domain. Everything in the domain would be a member of the set. But also everything in the domain would not be a member. Now, this set is special for many reasons, but one of the reasons is that you can use it to create inconsistent versions, let's call it that way, of other sets, as long as they are non-empty. This is a process we call Raudleization sometimes, okay? So if you take some set Y you can do its Raudalization, which I denote this way. This is only the intersection of the Raudly set with the set you want to transform, okay? And since the Raudly set is universal, then anything that is in Y is also there in Z. But then, since everything is not in Z, then this will generate another inconsistent set too. In particular, if you wanted to do this to the natural numbers, for instance, what you get is a subset of the natural numbers, which has all the natural numbers and also none of them. Okay, this is a very radical way to get inconsistent sets of numbers, and is the kind of thing I will be exploring a little bit today. Now, I'm not saying that all inconsistent sets of numbers have to be generated this way. I'm not saying that. I'm just taking this very easy way to get them and study some of the examples that might result from this kind of construction. Okay. Now, I mentioned to you that the model theory of LP has extensions and anti-extensions when it comes to predicates. And I mentioned that the membership relation was a special two-place predicate. So model theoretically, this membership relation holds or is true whenever the denotation of the set X and the denotation of the set Y is in the extension of this predicate that we're using as a membership relation. Okay, and false if these guys are in the anti-extension of this membership relation. Now, this is a very long mathematical expression. I will be conveniently writing it as X positive membership relation Y for the when the case is in the extension, and X negative membership relation Y. Okay. So this traditional symbol, for instance here, this traditional set membership symbol here is occurring at the model theory. It's at the meta theory. Whereas this epsilon here is the set membership relation of the object theory we're talking about, okay? And this is the kind of principle I want to play with in this approach. To say that in the object theory, X is a member of Y, if and only if in the meta theory, the denotation of X is in the extension of the denotation of Y, right? And negatively, for the case of the anti-extension. This is not entirely new. Lever has done a little bit of work using this kind of strategy as well, linking extensions and anti-extensions as a way to talk about inconsistent set theories as well. But keep in mind this kind of principle. Now, just because you are not in the, so if you're not in the extension of a set, then because the way the model is constructed, you have to be in the anti-extension, okay? But not conversely. And if you're not in the anti-extension of a set, then you have to be in the extension, but again, not conversely. This is because of two reasons. One is because we allow for inconsistency, and the other is because extensions and anti-extensions exhaust the domain. Now, to prove this, you have to use the disjunctive syllogism, which, as some of my colleagues have remarked in this conference, is invalid in paraconsistent logics and LP. Now, the proof is occurring at the level of the meta theory, not at the level of the object theory, so we might get away with it, at least for a while. Now, what happens with complements? Well, with complements, what we have is a very nice relation between extensions and anti-extensions, right? That yields the expected results. X is in the complement of Y, if and only if X is not in Y. Okay, so we will use this sort of complements law as a background. All right, so this is a version of naive set theory of LP, plus some elements that I want to use to talk about baby computability theory. Or maybe a better way to describe it is a modification of standard notions of computability theory that would be para-consistent friendly. Okay, it would allow us to talk about whether an inconsistent set is computable or not. So, oops. How do I go back? Okay. So yeah, I have an ontology of inconsistent sets with naive set theory of LP. Now I will talk about, we'll try to define a computability theory over it. All right, so we have extensions and anti-extensions around, so it makes sense to define some sort of characteristic functions that independently handle the extensions and the anti-extensions of a set. Some of them talk about whether something is a member, right? So for instance, you could say that a set is semi-decidable if and only if you have a characteristic function that will tell you whether something is in the extension of the set or not in the extension of the set. Call that the positive characteristic function. This is all about determining members positive, not necessarily non-members. That's a strong version of semi-decidability. You may have a weak version in which you can only determine whether something is in the extension, but not necessarily whether it is not in the extension of a set. But this is another possibility there. Dually, for the non-membership, you can have an independent characteristic function, this time a negative characteristic function, that will evaluate whether something is in the anti-extension of the set or not. And again, you could have a weaker version that in one of the cases is simply undetermined. This framework allows you to have that kind of distinctions in place. So if you put together semi-decidability and co-semi-decidability, you get a version of decidability. Okay, so sets are decidable here if they are semi-decidable and co-semi-decidable, which is nothing but saying I can recognize members and I can recognize non-members. Now here's a nice first little theorem in this toy model. You could say that the real or the full characteristic function of a set in a naive set theory can be three-valued, because you might have cases where something is in the extension but not in the anti-extension. Something is both in the extension and in the anti-extension, like the Russell set. Or something is not in the extension, but it is in the anti-extension. So you have three possibilities. This is very similar to the three values that LP has. It's logic. And you can actually prove something like the post-Kleene theorem, which told you that a set is decidable if and only if it and its complement are semi-decidable. And this is because of the way we have set up the complement laws that I told you before, right? And you also have some very basic and useful theorems in this adaptation of basic computability theory. For instance, if a set is decidable, then its complement has to be decidable. If you have two decidable sets, then the union has to be decidable too. And if you have two decidable sets, then the intersection has to be decidable too. And notice that when you use the characteristic functions in the way I'm doing here, what's going on there very much resembles the truth conditions of the connectives that I showed you in the model theory. But this is nice, very
Classical.
respectable, yes, very classical. Of course, if there are no weak notions of semi-decidability and co-semi-decidability, then there might be another weak notion of decidability. This is rather different than the standard approach. You might say that a set is weakly decidable if and only if it is weakly semi-decidable and weakly co-semi-decidable, or the same but for the complement. This is like sort of a borderline case of decidability that may arise in this sort of framework. And of course, this would give you another three valid version of a characteristic function whenever you introduce this weaker properties that we have been talking about. All right, so this is a very basic kind of adaptation of the framework that you would have to use if there's going to be inconsistent sets around. So let's talk about some inconsistent sets of numbers. The set theory might give us realizations of natural numbers. Okay, for instance, the first one is a set that has all the natural numbers and none of them. The third one only has the number 3 in it, but also 3 is not in there because nothing's there, right? And then you have the realization of the even numbers. So all the even numbers are there. They're also not. All of those, technically, they are subsets of n, right? The extensions of these realizations are the original sets that we have been realizing, if that's a verb now. And technically, if you look at the model, whatever the model has in it, the anti-extension of this realization has to be the whole model, the whole domain, right? Which is a very weird property. Now, as I told you, it's not mandatory that all inconsistent sets of numbers have to be realizations. You might obtain inconsistent numbers in other ways. For instance, you might talk about the typical weird sentences that in computability theory lead you to contradictory structures. So maybe some presentations of encodings of functions and diagonal arguments yield ways to define inconsistent sets of numbers too. But in order to use this framework, you have to show that these very different characteristic functions are actually computable, right? And that requires some notion of computability. So how do we do that? Fortunately, there are many different models of computability. One intuitive way to try to show that those characteristic functions are computable is to try to show that they are primitive recursive, right? You may do that. So for the sake of the argument, let's just assume that we have some primitive recursive functions in the background. Okay, maybe you have a function that tells you whether the number is 0 or not. You have a modus operation, a distance operation, all the constant functions. Suppose you have that. So you can show that the realization of the natural numbers is decidable. And this is very easy. Since every natural number is in it, the positive characteristic function is just a constant function. For every number, it will always say yes. And the negative characteristic function is also a constant function. For every number, it has to say this number is in the anti-extension, therefore not in the set. And that was the definition of being decidable, right? You have to compute both the positive and the negative characteristic functions. So this set is decidable, even though it is consistent. And you may use some similar argument for other realizations, right? So whenever you wanted to show, for instance, that the set of even numbers has a computable characteristic function, maybe you do that with some primitive recursive function. So you can use that argument for the case of the extension, and then for the case of the anti-extension, you might use this constant function argument too. And if your set was not, for instance, recursively enumerable, then maybe not even in this way would it be recursive enumerable too. Now, if we use this primitive recursive functions, we have to be very careful, because if we're not, then we can reach triviality very easily, right? So suppose you want to define a binary identity relation on the realization of the natural numbers, and you say, okay, two numbers are identical if the distance between them is 0. And if it is not 0, then they are not identical. That's one way we can do it classically. But if we do that, and the relation is inconsistent, that is, if it contains a tuple in the extension and the anti-extension, then we have that the distance between them is 1, but also we have that is not 0. So you can reach 1 equals 0 very, very easily if you do it this way. So since the spirit of these models is to treat truth and falsity independently, and also to treat membership and non-membership independently, it only makes sense that these positive and negative characteristic functions have different conditions or different ways to be defined. So you have to come up with a different condition or an independent condition to calculate the anti-extension. You cannot simply use the opposite of what you chose for the extension, right? So if you have those kinds of sets in mind, which are really inconsistent, then maybe thinking of them in terms of classical arithmetic doesn't match at all. What you really need is an inconsistent arithmetic that can talk or represent these sets. So for instance, and this is just about to finish, think about this arithmetic that Meyer and Mortensen call design over Rm, which is in the relevant logics family. This is some sort of cyclical model of arithmetic. You can take the relevant logic Rm, take all the piano axioms, and then add this modular equations there. 0 is equal to I applications of the successor function, and then other conditions for modularity. What you end up having in this kind of arithmetic, and this is the reason why it is inconsistent, is that every number is identical to itself, right? But also it's not identical to itself. And this makes sense in a circular model, right? Because if you are this guy, then you're identical to itself, but also after a certain amount of loops, you're a different number now, so you're also not identical to that number, right? But still, these are non-trivial theories. So 0 equals 1 is not a theorem, for instance. So this is a very famous example of an inconsistent arithmetic. And if you have that kind of structure in the background, then you might be able to define the positive characteristic function as, okay, the distance between the numbers is 0, right? So if you are here and you say this is x and this is y, the distance between them is 0. And then for the anti-extension, you might do something different. You can say, okay, is there an amount of successor functions that I can apply to reach the other number? And you could say, well, yes, I can apply as many successor functions as I need to get back here. So that number is a non-zero number, and that's a way to compute the anti-extension in this sort of example. But it very much depends on the kind of arithmetic, on the kind of model of arithmetic you have in the background, right? So the moral of the story is, if we want to show whether paraconsistent friendly characteristic functions like the ones I presented to you today are actually primitive recursive or not, that would need to be analyzed with respect to some inconsistent arithmetic, right? And authors of those inconsistent arithmetics often claim that all the primitive recursive functions are representable in the systems. And well, that might be so, but I think it makes more sense to think that those inconsistent arithmetics should come with their own versions of primitive recursion, because they have different phenomena going on there, right? And the framework that I presented to you today is only a toy model. It's by no means a finished theory of computability, but it kind of hints in the direction of what a paraconsistent computability theory should be. But it also shows that we really need to know more about the interplay between inconsistent set of theories and inconsistent arithmetics to make sense of the computability of these kinds of sets of numbers. Thank you.